Now it's time to use the atomic orbitals that we just generated and talked about in a molecular orbital picture for the bonding of, say, ethylene. So if we're looking at this carbon atom, then you realize that it has three bonding areas. So from a VSEPR perspective, it has to be trigonal planar. And you also realize then that the hybridization must be sp2 hybridized, which means that for this carbon atom to make bonds to all of the other groups, what it needs to use is three different sp2 orbitals. So that's how it makes its bonds. This carbon likewise also has three sp2 orbitals. At the same time, of course, there are four different hydrogen atoms in the molecule, and hydrogen atoms only use their 1s orbitals in order to generate bonds. So this is largely the framework that we're going to be talking about, at least in the first pass, with making the sigma bonds. However, what's not included in the sp2 hybridization for this carbon atom and this carbon atom is, of course, a leftover p orbital. And specifically, the way I was describing it first with the p orbital coming toward me and into the camera, this is a leftover pz orbital on this carbon, and likewise, there's a leftover pz orbital on this carbon as well. So we're going to finish up by talking about the pi bonding that takes place between the two pz orbitals here. So in terms of the atomic orbitals involved, the carbon first hybridizes by taking its s and mixing in two p's. Left over there's a pz. This carbon is doing the exact same thing to make bonds here, and the hydrogens are just using their 1s orbitals. Now, as we mentioned before, the carbon atom is going to be using its sp2 hybrid, so I'm going to go ahead and draw those. So the carbon atom then has three different sp2 hybrids right here, and then each of those sp2 hybrids is going to be interacting with another orbital. So up here I'm going to draw a 1s orbital that has to be with the same phase in order to interact. Likewise, this will be a hydrogen 1s orbital. And then over on the other side, we're going to draw the exact same thing again because the carbon on this side is going to be doing the exact same thing that this carbon was. Likewise, the hydrogen atoms involved are going to be using their 1s orbitals as before. And so if we're only imagining what the atomic orbital picture looks like, we've got the four hydrogen 1s's drawn. We've got the three carbon sp2 orbitals drawn here. We also have three more carbon sp2 orbitals for the other carbon. And then not drawn at the moment, but still present, are going to be the pz orbitals, which again come toward me and toward the camera and basically sit right here. So what do the orbitals look like that result from mixing all of these atomic orbitals together? So first I want to talk about the energy involved. You're going to have a carbon sp2 orbital, which is probably going to be a little bit higher in energy than the hydrogen 1s, but you're going to try to mix those two together. And for now, let's presume that the carbon is bringing one electron to the party, and the hydrogen likewise is bringing one electron. So when you mix these two orbitals together, that's going to create two new orbitals. And now that we're going to talk about molecular orbitals, we're going to describe them with Greek letters rather than Latin letters. Rather than s's, you would have sigmas. Rather than p's, you would have pi's. So this mixing of these two orbitals is going to create both a sigma bonding orbital, which is going to be lower in energy than the two orbitals by themselves, but it's also going to create at the same time a sigma star, sigma antibonding orbital that's going to be higher in energy than both of those at the same time. So the mixing of these two creates two new orbitals, and then when we go to populate these with electrons, of course the result is you're going to fill the bonding orbital, and there's going to be no electrons left over to fill the antibonding orbital, which is why a bond takes place, which is why a bond forms. Now, what does the actual structure of this orbital look like? Well, imagine you have a carbon sp2 drawn like so, and you likewise have a hydrogen 1s orbital, and you're going to mix those two together. And again, as always, when you mix together two orbitals, you need to create two orbitals, the sigma bonding and the sigma star, and the way you do that is simply by mixing them together and then flipping the phase and then mixing them again. So the end result is going to be something that looks like this, where you have elongated the bonding area because these two are mixing together in the positive direction, and this is going to be your sigma bonding orbital. But you're also going to flip the sign of this. So not only do you add it as drawn, but you flip the sign. You make this, rather than shaded, you make it unshaded. And the end result is going to be something that looks like this. And now you're going to have two nodes. Initially, of course, we had one node because of the S mixing together with a P, which had one node. And now when you mix that together and they add up, you get the sigma bonding orbital, which is good, and there's no extra nodes, it's just the one node that you had before. But when you flip the sign here and you subtract this from this, then you end up with two nodes, and that's going to be higher in energy, which is why it is the sigma star orbital. Naturally, the sigma bonding picture for the carbon atoms is going to be almost identical to the carbon and hydrogen, with some subtleties because, of course, we're now going to be using a carbon sp2 on both sides. So the image, what the orbital looks like, is going to have to be different. But the bonding picture is going to be identical, except here we have two orbitals of the same energy. Here, there's no reason to believe that those two orbitals would have the same energy. But the same idea. Mix together two sp2 type orbitals from the carbons, and you have to create a sigma bonding orbital as well as a sigma star antibonding orbital. Each one of the carbons is bringing one electron to the sigma bond that they are making, which means that the sigma bonding orbital ends up filled with two electrons, and of course the sigma star orbital ends up empty. So now, what does the actual bonding picture, the MOs themselves, what does the sigma bonding and sigma antibonding look like? Well, again, what you have to do is imagine mixing together an sp with an sp from the other side, one where they add together, and then you have to flip the sign of one of them. So you create the linear combination of orbitals, one where they are added together and one where they are subtracted from each other. So the sigma bonding picture is going to look like this. You're going to have a sigma bonding orbital that has two nodes. I usually call this kind of MO a Tootsie Roll. And the bulk of the electron density exists between the two nuclei. So you would imagine the carbon nuclei being here at where these nodes are, and the bonding area where the electrons are going to hang out is right exactly in between those two. And that's the sigma bonding situation, and it is quite stable. By contrast, of course, if you take this and subtract from it another sp2 in the opposite phase, then what you end up doing is creating one more node. That node is going to be exactly in the middle, so this is now going to be an antibonding orbital, but that node would be right where you most want the electrons to be, exactly in between the two nuclei. And because you can't have any electrons there, then the antibonding orbital is going to have larger lobes on the outside and smaller lobes on the inside. Something rather more like this picture. And again, the way you get there is simply summing together, an sp2 hybrid with another sp2 hybrid. You have to add them together first, in which case their phases are constructively enhanced, and then you have to flip the phase of one of them, in which case there's destructive interference of sort of the waveforms, and that gives rise to this three-node structure where there are relatively smaller lobes. This is good for bonding. You like the electrons to exist between the two nuclei. This is obviously bad for bonding. The place where you most want the electrons to be, the electrons cannot be because a node is there. Last but certainly not least, we need to go ahead and illustrate this for the pi system of ethylene. So we started by looking first at the carbon-hydrogen sigma framework, and though I only illustrated it for one of those, we know that all four of the CH bonds are going to be identical. Then the CC bond is fundamentally the same as this, with a little subtlety because of the nature of the orbitals involved, that it's carbon sp2 on both sides. But now we have something that's fundamentally different on the one hand and also kind of the same, and that is we're going to be using leftover p orbitals to generate this. So we're going to bring together two carbon pz orbitals, and as always we have a single electron in each of those pz orbitals. But now what we're going to do is mix them together to create a pi bond. So we're not doing a directional bond anymore. It's not going to be on the internuclear axis. It'll be above and below the internuclear axis. Subtle difference. Fundamentally the same picture, though, when you think about this from an electronic standpoint. So when you bring together a CPZ and another CPZ, what you're going to end up making is a pi bonding orbital, and you're also going to be making a pi star, so a pi antibonding orbital. And much as we had before, you're going to populate this orbital with two electrons, and that's going to be that, because that's all the electrons that we have. And of course, as you know from our previous linear combinations, the orbitals involved are going to be two p orbitals that we're going to mix together. Fundamentally, these orbitals should be drawn as coming toward me and toward you, but because that makes that difficult to see, I'm just going to sort of mentally rotate this. And so we're going to have a p orbital mixing together with another p orbital, and I'm drawing them in the plane of the glass so that it's easier to see. So those are the two p orbitals that we're mixing together. So what will the pi bonding system look like? Well, it'll look like these two lobes added together. What will the pi anti-bonding orbital look like? Well, it'll look like a node directly in between them. In other words, the pi bonding system is going to end up looking like this, with only one node in there, and this is going to be the pi bonding situation. And then the pi star, the pi anti-bonding scenario, is going to now have two nodes, the same node as before, as well as an additional node right here, where these cannot overlap in between. So this is going to be the pi star. So where are the carbon nuclei? Well, they're hanging out right here. So in the pi scenario, there's a lot of electron density that's above and below the internuclear axis, but concentrated between the two nuclei. Whereas in the pi star scenario, what you have is no electron density on the internuclear axis, because of course that's where a node is, but also no electron density essentially between the two. That's why this is an anti-bonding situation, and this is a pi bonding situation. So in other words, what we create when we make ethylene is we end up creating 4 sigma bonding orbitals between carbons and each of the hydrogens. We also create a sigma bonding orbital between the two carbons. Those are CsP2 bonded to a CsP2 to create that sigma. And we also end up creating a pi orbital as well. So this would be the p orbitals by themselves, and then we have a pi bonding situation as well. So the bonding for ethylene is 4 sigma bonds between carbon and hydrogen, a sigma bond between two carbon atoms, and then a pi bond between two carbon atoms. And that's the total molecular orbital picture for ethylene. Of course, also created in all of these is the corresponding sigma star orbitals. And there are 4 CH sigma stars, and there is 1 CC sigma star, and there's 1 pi star that's also created. These orbitals also exist, it's just that they are not filled. And so we don't necessarily need to think about them now, but they exist. And later when we start doing chemistry that involves reacting between molecules, then you're going to want to start thinking about these leftover empty orbitals, because those are going to be the ones that are willing to accept new electrons, and that will cause a rearrangement of bonds and atoms.